Okay, let's dive right into this. Welcome to this explainer session. Think of this as your exclusive insider's guide to absolutely mastering the Cambridge 9618 computer science exam. Today, we are taking what I like to call the street artist approach. Look, when you walk into that exam hall and sit down, that blank paper, that is your canvas. You need to make your mark with bold, confident strokes of creativity. But here's the catch. That creativity must be backed by a rock-solid underlying structure. Because without structure, well, it's just a mess. To illustrate this, picture a real past paper question in your mind, say from syllabus 9713 or 9618, asking you to trace the exact role of special purpose registers. I see two types of students tackle this exact challenge every single year. First, there's Alex. Alex overloads the page with raw facts, just totally brain-dumping every single thing they've ever learned about computer science onto the paper, with absolutely zero analytical structure. Then, on the other end of the spectrum, there's Sam. Sam rushes in, panic writing, completely missing the command word requirements of the question, and ultimately answering a totally different question that the examiner wasn't even asking. Both of them, they're losing massive, massive marks. And today, we are going to fix that. Look at that number, 15. I really need you to internalize this because this is where the high stakes of today's session become very, very real. The program counter, or the PC, and its associated special purpose registers account for approximately 15% of the total marks in Paper 2 of the computer science exam. 15%. Let that sink in. That is literally the definitive gap between a C and an A, or an A and an A star. Whether you are studying syllabus 0417, 0478, 0983, 0984, 2210, or our main focus today, 9618, the core mechanics of the central processing unit remain the beating heart of the assessment. Mastering this single topic gives you a massive tactical advantage. You aren't just memorizing a definition here, you are securing a huge foundational chunk of your final grade.
So, to secure that 15%, here is our agenda for today. 1. Core principles. 2. Technical methodology. 3. Critical analysis, and 4. Examiner warnings. Let's get moving.
Starting off with Section 1, Core Principles. We need to build your theoretical architecture, because raw facts just aren't enough. Now, what's really interesting about this slide is how it separates the top-tier candidates from the rest. Remember Alex from our earlier example? The student who just throws raw facts onto the paper hoping anything sticks? That is a deeply flawed strategy. Why? Because examiners aren't looking for a glossary. They are looking to see how the bricks fit together to build the house. The principal examiner reports consistently highlight that candidates who reference cross-topic connections achieve significantly higher marks. Think about it. The program counter doesn't just exist in a vacuum. It rests on precise definitions. Yes, it stores the address of the next instruction to be fetched. We know that. But the actual magic is in the causal relationships. The PC feeds the memory address register. The PC increments while the current instruction is being decoded. If you can clearly explain how the PC interacts with the data bus, the address bus, and the entire memory hierarchy, you are no longer just reciting isolated facts. You are demonstrating true high-level architectural understanding. I want to pose this question directly to you. Why do you think students find the distinction between similar concepts so incredibly hard? Seriously, why do candidates constantly blur the lines between the program counter, the current instruction register, and the memory address register? Think about it for a second. The principal and manager reports flag this specific struggle year after year like clockwork. It happens because students memorize definitions in total isolation instead of visualizing the actual data flow. They see static terms on a flashcard instead of a dynamic, moving fetch-execute cycle. To overcome that exact confusion, we have to look at how Cambridge actually grades you. The assessment objectives for the program counter target 3 distinct cognitive domains: knowledge and understanding, application, and analysis. And here is the insider secret. The exam aggressively prioritizes analytical depth over superficial breadth. This is where we introduce the Peel framework: point, evidence, explanation, link. Top students automatically structure their answers this way. They don't just state a knowledge point and stop. They explain the underlying mechanism, provide evidence from the specific scenario given, and then link it all back directly to the command word in the question. It is analytical depth in action. Moving right along to Section 2, Technical Methodology, let's look at how we actually extract those method marks. Knowing the theory is honestly only half the battle. Now we need a reliable procedural framework to actually extract those marks from the paper and turn your knowledge into undeniable grade-boosting points. Here is your 5-step procedural framework for tackling any complex question on special purpose registers. Step 1.
deconstruct the question. What exactly is the command word? Is it describe, evaluate, or trace? Step 2, extract the relevant data. Step 3, select your analytical framework, like the Peel method we just talked about. Step 4, execute with perfectly clear notation. And step 5, present it with the correct terminology. If our rushing student, Sam, had just followed step 1 and deconstructed the command word, they wouldn't have lost half the marks on their paper. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. So the crucial point is understanding the massive difference between providing a final answer only versus showing step-by-step working. In the examiner's playbook, this is famously known as the method mark strategy. Let's say you are asked to trace the values of the PC through a complex assembly language loop. If you only write the final binary address at the very bottom of the page, you get 0 marks if you made even one tiny silly arithmetic error along the way. 0. But if you show the step-by-step working, if you clearly show the PC incrementing, the branch instruction executing, the new address loading into the register, you get full method marks for the process, even if your final calculation is a bit off. This is literally how you transform red pen marks into green check marks. Let's apply this exact systematic processing sequence directly to extracting data from binary representations. First up, you identify the key elements. You look at it and ask, where is the opcode? Where is the operand? Second, you apply the relevant principles. How does the PC handle direct addressing versus index addressing? Third, you execute the analysis with incredibly clear working. Show the examiner the binary addition, show the bit shifts, leave nothing to the imagination. Fourth, verify your results. Take a step back and ask, does this final address actually make logical sense within the bounds of the memory provided? Finally, present it in the appropriate format requested by the question, whether that's hex, denary, or binary. This processing sequence is your ultimate safety net in the exam. Welcome to Section 3, Critical Analysis, where we transition to evaluative thinking for those absolute top-tier marks. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's do a quick mental exercise right now together. Think of a standard exam paragraph comparing the PC to the index register. Fact listing, which is incredibly weak and exactly what Alex does, just lists what the PC does in one sentence and then lists what the index register does in the next. That loses marks. Comparative analysis, on the other hand, is remarkably strong because it identifies similarities and differences. It actively uses comparative connectives like whereas, however, or in contrast. Top answers don't just dump facts. They support every single comparison with evidence drawn from the specific architecture given in the paper. You have to constantly ask yourself, am I just making independent points here, or am I actively connecting and contrasting them for the examiner? And this brilliantly illustrates exactly what higher-order assessment objectives demand from a top-tier candidate. Evaluative thinking requires you to really step back from the raw code. You must consider multiple solutions. For instance, why use an interrupt in this scenario instead of simple polling? You must analyze the trade-offs. How does increasing the bit width of the program counter affect a total addressable memory versus the actual hardware cost? You must acknowledge limitations, and most importantly, you have to justify your decisions with rock-solid evidence. If you only have 30 seconds left on the clock to speed write a perfect Peel paragraph, your explanation and link components must contain this kind of evaluative justification. When it comes to algorithmic thinking regarding the program counter, we really need to take those dense, wordy syllabus requirements and turn them into an actionable mental checklist. Number 1, step-by-step decomposition. How exactly does the PC change during a subroutine call? Break it down. 2, appropriate data structure selection. You need to fully understand how the stack interacts with the PC during that subroutine call. 3, efficient code implementation. And 4, rigorous testing using trace tables. Listen to me carefully here. Trace tables are your absolute best friend. If you can confidently track the PC's value line by line, step by step, through a complex algorithm, you have successfully mastered the examiner's ultimate test of logic. Finally, we've reached Section 4, Examiner Warnings. Let's look closely at avoiding the top 3 pitfalls. I want to shift gears right here and act as your personal academic coach. I've combed through the principal examiner reports, I've seen thousands of past papers, and I know exactly where otherwise bright, capable students just throw their grades away. Here are the principal examiner's top 3 mistakes. Please listen to these vigorously. Number 1, confusing cause and effect. Candidates so frequently write that the MAR fetches the address from the PC. No, absolutely not. The PC passes its contents to the MAR. The specific direction of that data flow is vital. Number 2, forgetting boundary conditions. Think about it. What actually happens to the PC if a jump instruction points outside the allocated memory block? You must check your edge cases. And number 3, answers not specific to context. If the question specifically gives you an embedded system scenario, like a microcontroller inside a microwave, and your answer starts talking about a desktop PC's complex operating system, you get 0. You must ground your theory in the scenario provided. This is exactly where Sam failed earlier by rushing and ignoring the context.
Okay, I am issuing a major examiner alert right now. Candidates consistently, year over year, confuse key terminology. So here is rule number 1 for any extended response. Always define your terms before using them. Never just assume the examiner knows what you mean by PC or MAR in your opening sentence. State it clearly right up front. The program counter, a special purpose register holding the memory address of the next instruction to be executed, and then launch into your brilliant analysis. It is a completely non-negotiable step for success. It shows rigor, it shows absolute clarity, and it locks in those foundational knowledge marks immediately before you even get to the complex stuff. Let me give you a really quick, actionable study tip for cognitive anchoring. Create a simple mnemonic for the program counter using the first letters of key terms. For example, points to coming, PC. It points to the coming instruction, not the current one. Simple little hacks like this prevent total panic in the exam hall and keep your thoughts incredibly structured when the pressure's on. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.